This part, of course, looks at one of the most intriguing aspects of particle physics: photons, the photoelectric effect, quantum, dribbled waves, and wave-particle duality. Water waves show the following effects: reflection, refraction, interference, diffraction, and they can all be explained as the ripples being a wave. The wave is also easy to see on the surface of water. Light also shows this effect, and therefore by extension, light is a wave, although at the time the nature of the wave was unknown. Maxwell put together a huge amount of apparently disparate information on the electric, magnetic, and electromagnetic effect into one simplifying theory and explained it that light is definitely a wave. What is light? Is it a wave or a particle? What you probably learned in secondary school is that light is an electromagnetic wave. This wave is transverse, meaning that the oscillations of the wave are perpendicular to the direction of the energy transferred. It has an amplitude and a wavelength. These are the defining characteristics of a wave. We are told that decreasing the wavelength with increasing amplitude allows a wave to have more energy. What we see, this happens with water waves. Electromagnetic waves become a whole spectrum of different wavelengths. Here is a quick reflection on the electromagnetic spectrum. This end has light of a longer wavelength, which are radio waves, and this end has a light of a shorter wavelength, which are called gamma rays. Visible light is part of the spectrum, which are evolved to see due to the abundance of it from the sun. Looking at the middle of the spectrum, with the red light having a longer wavelength than blue or violet light. Now carrying this information forward will make us to examine something that Heinrich Hertz observed in the 19th century. When ultraviolet light is shone on some metals, it will emit electrons. These electrons are regarded as photoelectrons. When placed on a vacuum, this emission can be observed as the circuit is completed. It is the electrons that reach the anode and current can flow. However, when we try this with a blue light or red light in a microwave, it would not work. How could this be possible? The first thing that may come to your mind is that the light is carrying energy, and when it comes in contact with the metal, this energy is applied to the electrons around the metal. When the electrons receive enough energy, it can overcome the electric circuit attraction of the positive nucleus and escape. We may have realized that all the electromagnetic waves that I've mentioned before have longer wavelengths in electroviolet light, so they carry less energy. So obviously, the spectrum will not occur when we are shining lower energy light onto the metals. What's so surprising about this result? Well, under the classical description of light under the transverse waves, we realize that the intensity of such a wave proportional to its amplitude squared. So, if we increase the intensity of the light, we should be able to get electrons released even with longer wavelengths without supplying enough energy. Unfortunately, this is not what happens. This effect, known as the photoelectric effect, simply does not occur with any wavelengths of light that are longer than their specific wavelength. When Einstein heard about this, he realized that a better description of light is needed. Because if the classical description of light as a wave was true, then turning on the intensity of red light should allow photoelectric effect to happen, but it doesn't. Einstein might have been inspired by Newton's view of light as tiny particles when he wrote his 1905 paper. He showed that the photoelectric effect can be explained if we say that light is composed of a fundamental particle known as a photon. These photons can come in different places, all sharing the same properties, such as being massless but different in one important aspect: their energy. Photons can be thought of as little packets of a discrete energy propagating through space and time. A photon has an amount of energy proportional to the frequency of the light. This can be formed in the equation with the proportionality constant K, which is actually the Planck's constant, a very tiny number. So, higher frequency light such as ultraviolet light is composed of photons of higher energy. Increasing the intensity of the light is like increasing the amount of photons that are emitted. It doesn't change the amount of energy in the individual photon. As seen here, there are photons of value 3 and photons of value 5. We have more of value 3 photons, so in total we are transmitting more energy if we decide to use this group of photons. However, this doesn't affect the fact that individual photons in group 2 have more energy. Whenever charged particles interact, photons are exchanged. They have no mass, no electric charge, no weak charge. Since they are responsible for all electrons and protons interaction, everything we do in our daily life, from moving a mass to running in a park, relies on the exchange of photons. Their energy contained in shifting in change in electric and magnetic field. Like all particles with no rest mass, photons travel at the speed of light. Maxwell put together a huge amount of apparently disparate information on electric, magnetic, and electromagnetic effects into one simplified theory and explained it all, that light is definitely a wave. Einstein assumed that light of frequency f contains packets or a quanta of energy hf called photons. The number of photons per unit area per unit time is proportional to its intensity, but the energy of a photon is proportional to its frequency and is independent of the light intensity. The minimum amount of work or energy necessary to take a free electron out of a metal against the attractive forces of the surrounding positive ions is called the work function of metal, which is denoted by letter W. The work function is related to thermionic emission, since this phenomenon is also concerned with electrons breaking away from the metal. Einstein's quantum model considers the photoelectric effect as the interaction of a particular electron with a particular photon, a one-on-one process. Incident photons are absorbed by electrons and the energy is used to eject them. If the energy of a photon is not high enough, the electron cannot escape. This explains both the threshold frequency and the almost instant emission of electrons. A further discussions of the details of the model based on conservation of energy produces the photoelectric formula and allows a discussion of how the maximum kinetic energy varies with incident frequency and how it can be experimentally be measured.